Okay, good afternoon, everyone. My name is Ruwei Lai, a student from Harbin Engineering University. Today, I will show you our new work, Disentangled negative sampling for cooperative filtering. The structure can be divided into 5 parts: backgrounds, related works, motivations, method, and experiments. First, I want to introduce the ICE recommender system. Now, ICE has been widely applied in various applications to address the information overload problem. And as a key recommendation technology, CF focuses on learning users' preferences from observed user item interactions. However, in many cases, it's not always possible to obtain high-quality explicit feedback, let alone a large amount of data to train a deep CF model. So implicit feedback, such as clicks, has become a default choice to train CF model. Well, in implicit feedback, each observed interaction is regarded as a positive sample, and a negative sample is selected from the uninteracted item, which calls negative sampling. So far, about 2 lines of negative sampling method had been proposed. The first is statistic negative sampling, which selects negative samples based on a statistic distribution, like a random distribution or a popularity-based distribution. The other line is hard negative sampling, which oversample hard negative items during the training process. Here, the hard negative items refers to those with a higher probability of being positive according to the model. Although existing work on negative sampling have achieved promising results, we argue that they still suffer from a common drawback. All of them ignore the fact that a user is normally driven by some specific factor of an item, but not all factors to interact with it. For example, a user may watch a movie just because it's director, while someone else may care more about the content. Without taking into consideration items' specific factors in negative sampling, existing method may fail to identify the most suitable negative samples to characteristic user preferences. So we propose to disentangle item factors in negative sampling. However, it's no trivial. We need to address 3 challenges. Before that, we give a definition of items factors. We call the factors that dominate a user decision-making relevant factor and the remaining factors irrelevant factors. The first challenge is how to disentangle the relevant and irrelevant factors. An item's relevant and irrelevant factors are different from user to user, so existing disentangled methods are inshuffled to disentangle the user-specific factors. Second, how to reliably measure the quality of negative samples, because the quality of negative samples depends on both items' relevant and irrelevant factors. The third is how to ensure the credibility of disentanglement. As we know, there is no ground truth to guide the learning, so it's very hard to ensure the credibility of disentanglement. To achieve this idea, we propose the disentangled negative sampling method, DENS, which consists of 3 parts to address the above 3 challenges. First, a hierarchical gating module is proposed to disentangle the relevant and irrelevant factor of items. It consists of a positive gating layer and a negative gating layer. The positive gating layer is used to disentangle the relevant factors of positive item with a user-specific gating operation. The negative gating layer is used to disentangle the corresponding relevant factor of negative items. We propose a factor-specific gating operation, which takes the output of positive gating layer as input. As for the irrelevant factor of items, factors other than the relevant factors should be regarded as irrelevant factors. So we use element-wise subtraction. Next, a factor-aware sampling strategy is designed to measure the quality of negative samples. Intuitively, a high-quality negative item with respect to the positive item could be selected by constraining their relevant factors while keeping irrelevant factors similar. To this end, we first need to measure the gap between positive item and candidate negative item in terms of relevant and irrelevant factors. Here, we adapt the differences between prediction score due to the consideration of efficiency. Next, we measure the quality of negative samples by maximize the gap in terms of relevant factor and minimize the gap in terms of irrelevant factor. In order to explicitly balance the different contribution of the two factors, we introduce a trade-off parameter alpha. A natural question here is why we do not use the absolute value of each gap. This is because if SR is negative, it's indicated that the uninteracted item VM is more likely to be a false negative and should not be selected. So we just keep it negative. If SI is negative, it's indicated that the uninteracted item VM contains more usable information and should be selected. So we also keep it negative. Then we will show you how to simplify the calculation process according to equations 3 and 4 and the distributive law of inner product. We can rewrite the equation 5 as follows. Note that the first two terms of the right-hand side of the equation 6 are the same for all candidate negative items and have no impact on the ranking of the quality of negative samples. So we can just safely move them and give the final factor-aware sampling strategy as follows, which is very simple and easy to implement. The final question in this part is how to choose alpha. Instead of setting alpha as a fixed parameter throughout the training process, we propose to linearly increase the value of alpha like a warm-up strategy. The third challenge is how to ensure the credibility of the disentanglement. Here we propose to adapt contrastive learning to supervise the disentanglement and introduce 4 contrastive tasks which supervise the disentanglement of positive item, selected negative item, relevant factors, and irrelevant factors. Due to the time and space limitation, more intuitive explanation can be found in our paper. We refer the BPR loss function to achieve the 4 contrastive tasks and calculate the contrastive loss by mean pooling of the 4 losses. Finally, we adapt the proposed DNS method as a negative sampling strategy and calculate the recommendation loss and use a hyperparameter gamma to weight the contrastive loss. We also give a capacity analysis of our method. It shows that our method does not significantly increase the time and space capacity of training a CF model. Finally, the experiment. As a negative sampling method, the first question is, how well does DNS perform compared to other negative sampling methods? We consider 5 datasets and 5 baselines and report the result in terms of 3 metrics. The result with light GCN are shown in table 2. Among all baselines, hard negative sample method performed better than the statistic negative sampling method. And by considering the relevant and irrelevant factor of items in negative sampling, our method DNS outperformed state-of-the-art hard negative sampling method. Second question we care about is how well does DNS improve negative sampling by disentangling relevant and irrelevant factors. We designed 3 experiments. In the first experiment, we studied the impact of a multitask weight gamma. Among all 4 data sets, the worst recall at 20 and NDCG at 20 are achieved when gamma equal to 0, where the disentanglement is trained without any supervision. Such result well verified the effectiveness of our proposed contrastive loss. Furthermore, we can observe that when gamma equal to 0.3 or gamma equal to 0.4, it is an optimal value and the model obtains the best performances. Too small gamma is not enough to guarantee the credibility of disentanglement, and too large gamma may contradict the main recommendation task, which will lead to lower performances. In the second experiment, we give a visualization of the learned relevant and irrelevant factors. We randomly pick a user and map the disentangled relevant and irrelevant factor of all positive and negative items into a 2-dimensional space. We observed that with the contrastive loss, the learned relevant and irrelevant factor are clearly separated. However, when we remove the contrastive loss, the relevant and irrelevant factor tend to be overlapped with each other. In the third experiment, we conduct an evaluation study to verify the benefits of different contrastive tests and report the results. You can find more details in our paper. We finally studied why the DNS can achieve better results when integrated with other CF models like MF, as shown in Table 5. When integrated with MF, DNS can also achieve better performances in most cases. However, compared with the more advanced CF model like GCN, the relative improvements brought by DNS over the other baselines are extremely limited. This observation suggests that the quality of the CF model affects the effectiveness of our proposed DNS. High-quality CF models enable learning more representative embeddings of user and items, which lies a more solid foundation for the idea of disentangling the relevant and irrelevant factors in negative sampling. We also studied the impact of different strategies for alpha and give explanations, which you can see in our paper. That's all. Thanks. Any questions?